We're going to start class today by doing questions 1 through 6 of your homework. And these 6 questions kind of lead us through a great progression to help our understanding of circular motion. The first 3 questions, we're going to get the circular motion, but the first 3 questions here have to do with non-circular motion. And all these questions have to do with the tension strength in a string. And the progression shows us the different jobs for the tension in a string, ultimately leading us up to the job of keeping an object in a circle. So question number 1, and this is posted out on Schoology, the worksheet is, that is, what must the tension in a string be if it is to move a 60 Newton object upward at a constant speed? All right, so if we draw our force diagram here, we've got tension going up and we've got the weight of the object going down. And our key here is this constant speed. Constant speed tells us that the sum of the forces is equal to 0. Well, T is in one direction and W is in the other direction, so I have to subtract them, so that the tension in the string is equal to the weight of the object, which is 60 newtons. And that makes total sense for us. Constant speed means equilibrium, which means the up force and the down force have to be the same. Question 2, what tension in a string must there be to hold a 6 kilogram object stationary? Well, again, we've got this idea of a stationary object, which means, just like constant speed in number 1, stationary means that the sum of the forces is equal to 0. Now we have the same force diagram as number 1, so I'm not going to repeat that. I've got the same fact that T and W are in opposite directions, so that the tension equals the weight. The only problem is I don't know the weight of this object, because 6 kilograms is actually the mass of the object. So I've got to work mass into this. So weight is just mass times the acceleration due to gravity. So I've got 6 kilograms. And to make the math easy, I'm going to say 10 meters per second squared for our G value, even though it's really 9.8, which is going to give us 60 newtons. Right? Now, the other reason I did that is to show you, basically we're talking about the same numbers here. I wanted there to be a little bit of symmetry here. 6 kilograms is basically 60 newtons. It's really 58.8, I think, but we can approximate to make it a little bit easier, because we're trying to get ourselves like a progression. So if that's what it's going to take to just hold that object there, 60 newtons, well then, if I'm going to accelerate the object upwards, then the force should be bigger than 60 newtons. So I've got the same exact force diagram as in question number 1, except the sum of the forces is equal to ma now. Well, again, T minus W is equal to m times a. So what tension must there be to accelerate this object up? Well, it'd be equal to the weight plus the mass times acceleration. And that, if we pause for a second, makes total sense. If there were no acceleration, then this term here would go away and we'd have tensions equal to weight. Well, that's what we had in the first 2 questions. Well, we don't have the tension equal to the weight here. It's equal to the weight plus some amount here that I have circled equal to mass times acceleration. Again, that makes total sense. If I accelerate this object a little tiny bit, then I'd have to I'd put a small number in here for A, and I would end up with a number just a little bit bigger than 60 newtons. But as this A number gets bigger, 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 I'm adding more and more to that 60 newtons to give us a bigger tension force. All makes total perfect sense. 60 newtons plus 6 kilograms times 3 meters per second squared gives us a tension force of 78 newtons. So if we compare that to the tension force to just make the object go at a constant speed or be stationary, it's bigger. And if I had a number between 60 and 78, say 65, it'd still be accelerating upwards, just not as much as 3 meters per second squared. And if I had a number bigger than 78, then the object would be accelerating upwards at a larger rate than 3 meters per second squared. So in question 1, we've got a job to just get the object moving at a constant speed for tension. Tension's job in number 2 is to hold the object stationary. Tension's job in number 3 is to accelerate this thing upwards. Well, tension's job in number 4 is to keep the object in a circle. So as soon, we've had keywords, constant speed, stationary, and acceleration. As soon as we see a circle, then automatically sum of the forces equals mv squared over r. Now it's a horizontal circle. Now when we talk about sum of the forces equaling mv squared over r, let's give ourselves a little diagram of a circle. Imagine that this circle is happening in the horizontal plane and we're looking down on it. Now, let's say that this object is always 2 feet from the ground. And we're looking down from the top on the top of the object, and it's traveling around a circle, let's say in, excuse me, in the clockwise direction. Well, at any given point, this thing wants to go straight. Our velocity vector is tangent to the circle. But in this particular case, a string provides a centripetal force. So the tension in the string provides a centripetal force that keeps the object in the circle. Now, when we talk about this, and this is a term we haven't mentioned, so this is new, right? So we're learning here, we're not just doing problems. These forces are in what we call the radial plane. Now, gravity would be working into this page, so it's not in the radial plane. The only thing in the radial plane, so we say radial, towards the center of the circle. The only thing in the radial plane happens to be the tension in the string. So the tension in the string's job, not like 1 and 2 to keep it in equilibrium, not like 3 to accelerate it linearly. Tension's job here is to accelerate this thing centripetally. So Ft equals mv squared over r. So what tension must be in the string to hold this thing? 6 kilograms times 4 meters per second, and I have to square that divided by a radius of 2 meters. Well, we need 48 newtons of tension to do that job. Now I'm going to ignore question 5 here for a second and just keep working our way logically. And then I'm going to go back to question 5. Well, let's think about this. The faster and faster and faster and faster this thing goes, the more tension that is going to be required to keep it in the circle. It's harder to keep something going super fast in a circle than it is to keep something that's not going very fast. So let's use numbers. People like numbers. Well, what if we change this speed from 4 to 6? Then Ft would equal 6 kilograms times 6 meters per second, and I'd have to square that, divided by 2 meters. Well, that's 108 newtons. So there's more force needed because the speed went from 4 to 6. Well, if that speed went up to 8 meters per second, we'd need even more, right? That force, that tension force would be greater. How do I want to write that? If the speed went up to 108, therefore the tension force, if the speed went up to 8 meters per second, the tension would be greater than 108 newtons. And the more and more and the faster and faster I got this going, the more tension there is in the string. But remember how misleading, we did this in my car the other day. Remember how misleading this is. It should really be, this equal sign should again be needs to be. So the tension needs to be mv squared over r to keep the object in the circle. We don't always get what we need. So in the case of question number 4, when v equaled 8 meters per second, well, I'm sorry, when V equaled 6 meters per second, if V equals 6 meters per second, then the tension force needed was 108 newtons. Well, some strings can't provide 108 newtons. If the amount needed, which is over here on the right side, exceeds the tension that can be provided, the object can no longer stay in the circle. In which case, that's our answer to question number 6, the object goes tangent. Flies off in a straight line because that's what it wants to do. Remember, this velocity right over here, the object always wants to go straight. The string is preventing it from going straight and causing the circle. But if the string no longer can cause the circle, then the object will go in the straight line that it desires. Well, question 5 asks, how big of a speed can we get if the tension can go all the way up to 400 newtons? Well, again, sum of the forces equals mv squared over r. Again, how come? Because I've got this word circle. Well, we're trying to find that maximum speed. So we solve this thing for v, sum of the forces times r equals mv squared. So r times the sum of the forces divided by m square rooted is equal to v. What's the radius? Well, the radius was going to be 2 meters, the same thing as it is in question 4. The maximum force for that tension is 400 newtons, and we have this 6 kilogram object. And then we got to take the square root of that, and that's our answer. So we've got job progression for our tension. Move upward at a constant speed. Keep the object stationary. That's question 1 and 2. The tension would be equal to the weight. If I want to accelerate that thing upwards, it's going to have to be greater than the weight. That's 78 newtons, as in question 3. And then we've got a whole new job. Whole new job in question 4. We got to keep that thing in a circle. How much force is needed to keep it in a circle? 48 newtons for question 4. The string has a certain amount of potential tension. How much can it withstand? And that's going to give us our maximum speed. If the object goes over that maximum speed, it no longer goes into a circle. Instead, it flies off tangent.